not always true. But also we can have more extreme examples like this one. And this is a kind of real-life situation in which maybe you are training some model for making decisions or choices in the context of autonomous vehicles. And maybe in the training sample, we don't have this kind of perturbations. That is just some kind of trick of light. If you have, and maybe you have it at the test time, we have this game of light. The algorithm may perform an incorrect decision, and that can be dangerous for the user of this kind of algorithms. And also we can have situations in which we have the same kind of label for the same kind of data, but in different contexts. For instance, in this image, we have this human photograph of a human being, and here we have a digital version of the same, well, maybe it's a digital version of this drawing, and here we have some kind of more artistic drawing, a meme. And can a computer decide if you train your computer model by this kind of stuff, more artistic like photographs, and all the training samples have arised from this kind of data? Can you devise a computer algorithm capable to correctly make labels to say this is a human being? Let's say that is the label. Can work well if you have some kind of digital versions of that. It's not obvious, but we have a change in the distribution. If you have more of these ones in the training set, in the training time, and more of these ones in the test time, you will have you are trying to perform an out of distribution estimation, and that is not does not satisfy the actual conditions for which most machine learning algorithms are devised. Okay. So here is our proposed solution. It's just a work in progress to contribute a little to overcome this kind of limits that currently computers face. And it's based on a classical concept that is the Boltzmann machine. The general Boltzmann machine is a kind of algorithm very similar to neural networks. In fact, they arise more or less at the same time, the same of the 80s or so on. That's the past century. But the difference between a Boltzmann machine and a feed-forward neural network is that the topology can be closed, so we can have loops, logical loops, and this can be very helpful if you are capable to train that kind of systems. And I will try to explain why these loops can be useful. Let's imagine a simple logical gate, like an AND gate, or an OR gate, or so on. And suppose that these labels x0, x1, and x2 represent the possible bits for a logical gate. These kind of logical gates are the basics for any computation in a logical machine, just by combination and connection of these kind of logical gates. So let's propose this, define this operation for the definition of any bit, given the other bits in the topology. All of them are connected by this structure, in which we have these queues that are actual connections between bits, and the x are the bits, and we have this kind of bias parameter that is the response of the gate of the bit in the absence of any connections. And we just round it just to have at the end an integer value, 0 or 1. And playing a bit with this bit, playing a bit with this structure, we can find solutions. For instance, to construct this is an AND gate, I believe, yeah, an AND gate. So by this selection of parameters, we may have an AND gate that always gives the correct. If you decide in a bit arbitrary way that x2 is the output of the gate, then this selection of parameters will give you a correct answer 100% of the time, independent of for any choosing values for x0 and x1. On the other hand, if you, with this same selection, You can have, you will retrieve the correct values in the inputs 100% of the time. If you have one bit at the output, if you're told, I have a yes at the output gate, gate, yes. Then I can go to the other. I can perform the inverse operation, so I can reverse the logic and say that which bits are yes.
Sorry, just to be sure that I understood correctly.
Yeah.
But I actually don't see why this kind of learning solve the out of distribution.
I will arrive at that. I will go to that. I'm going to that. No, I'm talking here. We're talking of three problems here. We have the energy problem. We have the NP versus the NP and undesirable problem. And we also have the out of distribution problem. And this, I'm not saying that can be solved. I'm saying that they can maybe be alleviated in some regard with this kind of methods. Let's start with the logical part, okay? And then I will move ahead to this out of distribution question. Very good question, however. So
here you are learning, actually you are imposing that the evolution of your machine is capable of reproducing the distribution of the OR, N, and XOR function.
Yes, in a reversible sense. In a reversible sense.
In a
reversible sense. Yes.
Oh, okay.
In a reversible sense. So that can, if it is reversible, then it's not subject to the Landauer limit in principle.
But I don't understand in which sense this is reversible. So you put the output, you get the input.
Suppose that your bits are fluctuating.
Mm-hmm.
If they are fluctuating, let me finish. I also go into that, and then we can discuss that. Okay?
That's not invertible, right? Am I getting it right? The round function is not a...
The round function is not reversible.
Okay.
Yes, that's right. That's right. But that is just part of the construction. But the probability distribution that you can construct over that can be. We can discuss that. Okay. Let me show you. Okay, let's try this one. Suppose you have an XOR gate, and you can try the same trick, just to very simple arithmetics. In fact, if you proceed by this is just arithmetic. This is not anything special at this point. But if you try to do the same trick for the XOR gate, at least for this topology, in which you don't have this any internal unit, and you try to find the values that give you something similar to this thing, to this at least 100% accuracy in some direction of the information flow. That is not possible and, for this topology. And in fact, you can prove that because, as you can see, these kind of parameters arise from this part of the sigmoid, okay? And this define a set of inequalities, and these inequalities obviously define some space in the real and integer and 0-1 domain. So that space define an integral, and you can define probability functions or normalize over a substrate. You can see this space like I forget the name that you're doing probability to support. You can use it. You can use this space like a support for a probability distribution, and you can show very easily that these inequalities do not lead you to a closed support, and you cannot normalize a probability distribution. How you can try to construct a probability distribution from these deterministic inequalities? Well, you can treat them like observation or like conditions. And we have quite an old principle of probability and stochastic processes and statistical mechanics named maximum entropy principle, which you can define a probability distribution given some set of observations just by maximizing the entropy, and that will be let's say, the less biased possible distribution that is consistent with the observations. If we treat these inequalities like observations, then we can use this maximum entropy principle to define a probability density or distribution in this case, because we have also integer values. But for this topology, that is impossible. For this one, it is. For this one, it is. It leads us to a more complex set of inequalities, but this has solutions in the integer real space, and we can also try to do that, but this at least show us that given a topology and given a certain amount of data, it can be possible to find a space in which we can define a probability distribution that is consistent with data in the sense of the maximum entropy principle. Okay, and this can be done also for the unsupervised case. For instance, this should be unsupervised. Suppose now we have now a probabilistic machine in which the bits fluctuate by some mean. They are fluctuating bits. That temperature makes them fluctuate, and they can go anywhere around this loop topology, and then you have a reversible probabilistic system. And now we can proceed by doing the actual algebra for the inequalities. But maybe we can